Okay, now we're going to try some miscellaneous equations here that involve maybe some factoring, some identities, a little bit of both, maybe one or the other. And there's all kinds of possibilities, okay? So this is where you just play around, kind of like when you're trying to prove an identity, okay? So if you look at this here, there's a double angle inside here. This is sine of 2x, and so right away it tells you maybe you could use a double angle identity to solve it, and that's especially the case when this one is not a double angle, right? And so by using the double angle identity, you can get this thing into a single angle like this. So if you remember, sine of 2x is equal to 2 sine x cosine x. I guess I could write this down here. And that is just the double angle identity for that is the double angle identity for, and I better write identity here. That's the double angle identity for sine. And so I'm going to use this to change this into 2 sine x cosine x is equal to square root of 2 sine x. And now I can use factoring. So I use the double angle identity, and now I can bring this over and factor out the sine. So I'm going to bring that over. Set it equal to 0. So once it's set equal to 0, if I can factor this, then I'm going to be able to split it up into two basic equations. So that's sine x, and then this is going, I'm factoring out the sine x, 2 cosine x minus square root of 2 is equal to 0. So now either this is equal to 0 or that is equal to 0. So either sine x is equal to 0, and this clearly is going to solve into cosine x equal to square root of 2 over 2. So these are both special angles. So sine x is equal to 0 here, and you can write it as just k pi. And this one, square root of 2, it's like right about there, and it's the 40, this is a pi over 4 angle, and the other one occurs down here, which is 7 pi over 4. So I get x is equal to pi over 4 plus k times 2 pi. X is equal to 7 pi over 4 plus k times 2 pi. And then these would be the solutions to the equation, okay? Now let's try this one here. If you look at this one, I have the double angle again, okay? So I'm going to use a double angle identity and see what happens. So if I do that, this becomes 2 sine x cosine x times cosine x is equal to sine x. Okay, so this thing I could write as 2 sine x cosine squared x is equal to sine x. Okay, can you see how to solve this here? Okay, I can, if I set everything equal to 0, right, then I can factor out the sine and split it up. So I would get 2 sine x cosine squared x minus sine x is equal to 0. And now the sine x can be factored out. So sine x is equal to 2 cosine squared x minus 1 is equal to 0. Okay, so this would be, I just set each one equal to 0, so I get sine x is equal to 0, and this one here would be 2 cosine squared x minus 1 is equal to 0. Okay, this one, of course, is just x equals k pi. And then this one, I could factor it again into square root of 2 cosine x minus plus 1, square root of 2 cosine x minus 1 is equal to 0. And then these actually become cosine x is equal to negative square root of 2 over 2. And this is cosine x is equal to the square root of 2 over 2. So if you're not sure why that is, let me show you down here. So if I have cosine square root of 2 cosine x plus 1 is equal to 0, then I would get this is equal to negative 1 cosine x is equal to negative 1 over the square root of 2, multiply top and bottom by the square root of 2, and then you would get negative square root of 2 over 2. Okay, so that's how I went from here to here. Okay, so now we can find these, right? The negative square root of 2 over 2 for cosine is this 45 degree here, and that would be 3 pi over 4. Maybe I can zoom in. And then the one down here would be 5 pi over 4. Okay, and then for these, clearly I got the pi over 4 and the 7 pi over 4. So I would have pi over 4 plus k times 2 pi. X is equal to 3 pi over 4 plus k times 2 pi. X is equal to 5 pi over 4 plus k times 2 pi. X is equal to 7 pi over 4 plus k times 2 pi. Okay, and those would be the solutions. Okay, and I was thinking you could almost simplify this into something like k times pi over 4, but you actually can't, because it does skip over there, and it skips over there, skips over there. Okay, so you have this and that down there as your solution to that equation. Okay, so I have two more here, and so maybe zoom out, kind of zoom in as we go along. Okay, and notice what I have here is double angle identity for cosine, right? Does that make sense? And this is a little more tricky, okay? And instead of writing on here in case we need extra room or whatever, let me just remind you that cosine 2x has several different identities. It could be cosine squared x minus sine squared x. It could be 2 cosine squared x minus 1. It could be 1 minus 2 sine squared x. Okay, so you have these three possibilities. So what you have to do is look at this and kind of decide which one of these would be most helpful. And you could maybe pause the camera and try each one and see which one helps. You could probably do multiple things, but when I look at this, I'm thinking this one would be most helpful, because I would have everything in terms of sine. It'd be like an equation of the quadratic type. Everything would be in terms of sine. So I'm going to choose that one. So this I could write 1 minus 2 sine squared x minus 1 is equal to sine x. And if you look, these actually cancel out, just leaving me with negative 2 sine squared x and then a sine x. Okay, so I'm going to move this over to the other side, get everything equal to 0. And basically, Zechariah, do not interrupt, please. Okay, it was already an interruption earlier when the food came to the door. So let Dad finish, okay? So, because this is an especially long video, I have 4 identities. Okay, my son was calling for me. You know, if you don't have a constant term to solve the quadratic equation, just pull out a sign. In fact, I'm going to pull out a negative sine x. And then what I get is 2 sine x minus 1 is equal to 0. So then I get these 2 equations. So negative sine x equal to 0 is just the same as sine x equals 0. And then this one is just sine x is equal to 1/2. So this we've already seen as k pi. Sine x equal to 1/2 would be pi over 6. And this one over here, 5 pi over 6. And so I get x is equal to pi over 6 plus k times 2 pi. X is equal to 5 pi over 6 plus k times 2 pi. And that would be the solution to this. Okay, and I'm using double angle identities again, but this time for cosine. Okay, now this is an interesting one. This last one here. You would probably think, oh, you know, I could use the Pythagorean identity here to change one of these into the other, and it wouldn't matter which one. You could do that, and it wouldn't matter which one that you did, because there's no linear term, and then what you get at the end you're going to be able to factor and solve. But if you have a cosine squared and a sine squared, what kind of comes to mind is this identity, right? Which would become this. And so what I'm going to do is I'll bring the sine squared to the other side and then kind of write it on this side. So it would be cosine squared x minus sine squared x, and then write that on the other side. It's equal to negative 1/2. And the reason I do that is because now this becomes that, right? And that's kind of nice. Because what I get here is a multiple angle question. This is the first one where we have a multiple angle, but it's a special angle, right? And so very easy to solve. So cosine x negative 1/2 is right here. So you have the 2 pi over 3, and the one down here is 4 pi over 3. Okay, but now it's a special angle. It's 2 cosine x is equal to that. Okay, so I'm sorry, it's cosine of 2x equal to that. So we get 2x is equal to 2 pi over 3 plus k times 2 pi, and that would be x is equal to 2 pi over 6 plus k times pi. And this would be 2x is equal to 4 pi over 3 plus k times 2 pi. And so I would get, and what I'm pausing here because I'm noticing these can reduce down. So this is 4 pi over 6 plus k times pi. So I could have rewrote these as pi over 3 plus k times pi, and 2 pi over 3 plus k times pi. Okay, but that is a nice way of solving it. And what you might want to do is grab a sheet of paper and use the Pythagorean identity and solve the quadratic equation, and you should get all the same solutions. Kind of neat to see that. So these are just several different equations using identities, factoring, kind of all of it together. Okay, and then we have one more. Oops. What we're going to do is we're going to see how we can solve these using the sum difference identity. Okay, sometimes that might be useful.